So now come to the binary system. So in a binary system in which the two metals are completely soluble in the liquid state and solid state. What does it mean? I mean, you would have the alloy in which you could have the uh, l- in a liquid state you can easily combine, easily you can mix. Okay, easily solubility in only liquid state, but they are not in solid state. But what the kind of example that we have taken here is for the complete solubility in liquid state and solid state. In the both the condition they are soluble to each other. Okay. So the main condition for the unlimited solubility in the solid states are the alloy system should satisfy the Hume-Rothery rule. I have already made you know what is rule. See here. Where it is? Yeah, this one. Hume-Rothery rule. So if you have they satisfy this rule, what they say. Suppose these three criteria. First one is atomic size factor that must be less than or 50%. The material that are going to mix together that must have the atomic size less than 50%. Okay, the difference of I mean difference of these two elements atoms have radii less than 50%. Okay, so first one, the second one is crystal structure. So both have the same crystal structure. Both solute and solvent metals should have the same crystal structure. If BCC, FSC, or HCV, both should have the same, so that it will satisfy the solubility criteria. Okay, and this is the electronegativity, means the difference in the electronegativity between the two elements should be small. If the electronegativity is small, then it will be easily soluble in each other. Okay, and valency, the valency means whatever the kind of the electron is free in the outer orbit is known as your valency. Okay, so the same valency or similar valency must be there so that you have a better solubility in two component. Okay, so keep in mind this rule. Okay, Hume-Rothery rule. So once they have satisfied, yeah, the main condition for the unlimited solubility in the solid state are that the alloy system should satisfy Hume-Rothery rule. Okay, so suppose if this is a condition, if that condition has already been satisfied, then you can proceed further. This type of the alloy system is formed between copper and nickel, copper and gold, copper and platinum, iron and nickel, iron and vanadium, bismuth and tin, and cobalt and base alloys. So these are just example. Okay, it could be more, but this is a few examples. So the following are the characteristics of this type of alloy system. What are the main characteristics? Okay, so due to the unlimited solubility in the binary system, no eutectics exist within the system. I already made you know what is eutectic in last class. Okay, so upon faster cooling, the structure, and if anybody has doubt, then can ask me. Okay, upon the faster cooling, the structure of the solid solution type alloys will be of the well defined. Okay, dendritic characters because of the lack of homogeneity. Okay, of composition of the crystal. This formation of the system alloy within the crystal is called the coring or dentering segregation. This type can be removed by the annealing. So this is basically what is coring. Coring means, once you have once you have given the time to the system so that they will cool down. So once they are cooling down, they have a nature to solidify. So how they will solidify? First, they will have a kind of the nucleus here, suppose, and according to around of this nucleus, nucleus what means, accumulation of some kind of atoms exist. Okay, once they have two or three atoms collide together, and around this the more atom will start colliding. This is the formation of your solid state. So starting of your solidification is known as your coring. Okay, so this is your coring, and so they will I mean you know they have a kind of a different structure. So if you want to remove and you want to make them all the crystal in one sense, then you can. In engineering means you just need to heat up all the solid before the recrystallization. You cannot melt the solid, but you just need to reach the recrystallization temperature where they will kind of and now you are keeping them to cool down. Okay, that is known as your ending. In your environment temperature, I mean, if you have raised the temperature of solid and now you are making them to cool down, have different ways as well. Suppose you are just, you know, keeping at the top temperature or at a high temperature, and now you're just keeping into the water. It means they will, you know, cool very fast. So in this process you could not have released that kind of other things, okay, because that is known as quenching. So annealing means you are just reaching the temperature to the recrystallization temperature, and once you have reached the recrystallization temperature, now you are keeping them to release their heat into the environment, and then they are keeping themselves, they are cooling themselves. Okay, this the process is known as your annealing. Okay, so the variation in the mechanical properties in this system is a small with respect to the variation in the alloy composition. Okay, so whatever the kind of the mechanical properties, okay, so they will not vary in this sense as compared to the alloy composition. The variation in the physical properties like the electrical and corrosion resistance all are fabricated properties like the rolling, forging, and stamping. Etc. Or it could be may changes greatly with only slight variation in the composition. Okay, so if you know we talk about the mechanical properties, that will not change with slight change in your composition. But as far as physical properties is concerned, they will change it highly if you change the composition very small amount. Okay, so alloys which form homogeneous solid solutions are easily worked and are widely used as an engineering material. So this is the kind of the things that are being used, the kind of the material that are being used across the world very frequently as engineering material. Okay, so the cooling curve shows for the pure copper 100%. Pure copper means 100%, right? Content in the flat portion during which the complete solidification takes place at the constant temperature. When 20%, let's see here in the figure diagram, right? This is the diagram. Let's see, this is the coring. This is coring structure, or you can say code structure. Okay, the same manner as we have seen before. What is the cooling curve and how we can draw the phase diagram? You can see at the different temperature you have a different value. At a different temperature you have a different value. At a different temperature, and at all temperature, suppose you have a T1, then you would have the temperature composition of like this. At this composition you would, and if corresponding to the temperature 1, only this particular temperature, this particular composition shows at a solidus liquidus line. But if you would decrease the temperature or increase the temperature, suppose T1 you have reached here, it means you are now only on, you have liquid state. But if just you have decrease, suppose you are here, it means you are just reaching the solidus liquidus line before that composition, means it would be on different composition. Here you can see, so here in between this 40 and 60, okay, here it is 20 and 40. Okay, if we talk about the nickel, if we talk about the copper, then here you are 60 to 40, here 80 to 60 means. So the composition of the constituent material has changed. So this is how we you know get the idea. And at a different temperature, in a different composition, you would have the different you know structure as well. As you can see here in the solid state, if 20% nickel, the structure is like this. Okay, 23% solid solution, then you have like this structure. If you have the liquid 20%, okay, nickel, here you can see it is 20% nickel. Okay, 20% nickel and 80% copper. But at what temperature? The temperature could be like T1. At T1 you are here, see here. For if we talk about this particular diagram, then we are at 20% nickel and 80% copper. And corresponding to this constituent, you can draw the horizontal, vertical line. And now at what temperature you are seeing, you just need to draw a horizontal line. Whatever the intersection point that you get, that is your. So as you can see, this particular point, this particular intersection point is just above the liquidus line. It means whatever the phase that you have taken at that particular temperature is in your only liquid state. So this is the state which is liquid state. Suppose the same composition, but you have lesser temperature. Suppose this temperature is here. Now you can define what is the. It means the same. I mean, it is the idea that at the same composition, same constituent, you are having the different state, because you have changed the temperature. Now you suppose you have the temperature T4 here, right? So at T4 you are only having the solid state, though you have not changed your composition. But why? You have kept the same composition, but you have decreased the temperature. Okay, so and obviously it is obvious that when the same liquid is the liquid at the same in the same composition and in the same constituent, if you have decreased the temperature, it will solidify after some time. And now suppose suppose you are having at the temperature 3, right? The same composition, 2080, right? 20% nickel and 80% copper. Now at the temperature 2, sorry, temperature 3, what is the intersection point? Intersection point is this one, right? So this intersection, what it suggests? It suggests means you are having not only liquid, not only solid, but you are having the composition of both two, or you can say the two phase region. It means some solid is also there and some liquid is also there. But if you are concerned about how much percent of there is, then you can just apply the lever rule. Okay, so how can apply the lever rule? Simply just you need to draw the point. It is, suppose it is a, it is, sorry, no, yeah, a, this is your B, and at the end point, what is the end point? End point is here, this is your C. Now you just need draw this line and this intersection point. So A, B, C you have drawn, and now you need to just identify the three things. And now what you can do, the weight percentage of, you can suppose draw what is the percentage of nickel here, okay, and what percentage of nickel here, right? Similarly, what percentage of your copper here, okay, and what percentage of copper here, and just multiply those both things, just multiplying these terms, and overall this term multiply with 100, as we have discussed in the lever rule. So we can easily calculate what I mean, this is the total percent, the total 23% of the solid solution, right? So here 23% of solid solution means overall, I mean, whatever this is overall, right? In overall 23% at this particular temperature and this particular composition or constituent. But you are suppose need to know this is solid and this is liquid, right? So how much percent weight percent by the liquid is present there, so solid is there, then you can apply the lever rule and then you can get the value of these all solids by weight fraction and by the weight of your liquid. Okay, so you can easily calculate by applying the lever rule. Okay, so this 23% doesn't mean the solid or liquid. This is the overall percentage of the two-phase system. I mean, in this region, at this particular constituent, at this particular, uh, you know, ratio, what is the value of the solid solution at particular temperature T3? So keep in mind. Okay, so these are basically area. So by lever rule, we can apply. With the help of the lever rule, we can calculate the value of how much weight fraction the solid and liquids are there at particular temperature. Temperature and constitution both are important, because if any graph you are representing, or any graph that you are concerned about, you must need to know what are the given at the x-axis and what are the given, what the component or what the factors that are given to the y-axis, and you need to combine them together, and whatever the intersection point there is, that will define your property. Okay, similar to that. So here you can see at this particular point, yeah, this diagram, what this diagram shows. I mean, at this particular point means, I mean, as you can see, 20% nickel, 80% copper, the same constituent as I have taken all the example. But what is the difference? You have here means you are at this particular temperature. It's a, what is the temperature it would be, but that would be your solid state, because it's under the solidus line. This is your solidus line. This is your liquidus line. So what are the things that we are here below that solidus line? Everything would be in solid state. And what are the things that are upper to the liquid state, liquidus line, that would be in liquid state only. Okay, I hope you got the idea, right?